In mathematics, a finite subdivision rule is a recursive way of dividing a polygon or other two-dimensional shape into smaller and smaller pieces. Subdivision rules in a sense are generalizations of fractals. Instead of repeating exactly the same design over and over, they have slight variations in each stage, allowing a richer structure while maintaining the elegant style of fractals. Subdivision rules have been used in architecture, biology, and computer science, as well as in the study of hyperbolic manifolds. Substitution tilings are a well-studied type of subdivision rule. Definition: a subdivision rule takes a tiling of the plane by polygons and turns it into a new tiling by subdividing each polygon into smaller polygons. It is finite if there are only finitely many ways that every polygon can subdivide. Each way of subdividing a tile is called a tile type. Each tile type is represented by a label. Every tile type subdivides into smaller tile types. Each edge also gets subdivided according to finitely many edge types. Finite subdivision rules can only subdivide tilings that are made up of polygons labeled by tile types. Such tilings are called subdivision complexes for the subdivision rule. Given any subdivision complex for a subdivision rule, we can subdivide it over and over again to get a sequence of tilings. For instance, binary subdivision has one tile type and one edge type. Since the only tile type is a quadrilateral, binary subdivision can only subdivide tilings made up of quadrilaterals. This means that the only subdivision complexes are tilings by quadrilaterals. The tiling can be regular, but doesn't have to be. Here we start with a complex made of 4 quadrilaterals and subdivide it twice. All quadrilaterals are type A tiles. Examples of finite subdivision rules. Barycentric subdivision is an example of a subdivision rule with one edge type and one tile type. Any triangulated surface is a barycentric subdivision complex. The Penrose tiling can be generated by a subdivision rule on a set of 4 tile types. Certain rational maps give rise to finite subdivision rules. This includes most lattice maps. Every prime, non-split alternating knot or link complement has a subdivision rule, with some tiles that do not subdivide, corresponding to the boundary of the link complement. The subdivision rules show what the night sky would look like to someone living in a knot complement. Because the universe wraps around itself, an observer would see the visible universe repeat itself in an infinite pattern. The subdivision rule describes that pattern. The subdivision rule looks different for different geometries. This is a subdivision rule for the trefoil knot, which is not a hyperbolic knot, and this is the subdivision rule for the Barycentric rings, which is hyperbolic. In each case, the subdivision rule would act on some tiling of a sphere, but it is easier to just draw a small part of the night sky, corresponding to a single tile being repeatedly subdivided. This is what happens for the trefoil knot, and for the Barycentric rings. Subdivision rules in higher dimensions. Subdivision rules can easily be generalized to other dimensions. For instance, barycentric subdivision is used in all dimensions. Also, binary subdivision can be generalized to other dimensions, as in the proof of the Heine-Borel theorem. Rigorous definition. A finite subdivision rule consists of the following. 1. A finite two-dimensional CW complex, called the subdivision complex, with a fixed cell structure such that is the union of its closed two cells. We assume that for each closed two cell of there is a CW structure on a closed two disk such that has at least 2 vertices. The vertices and edges are contained in, and the characteristic map which maps onto restricts to a homeomorphism onto each open cell. 2. A finite two-dimensional CW complex, which is a subdivision of 3. A continuous cellular map called the subdivision map, whose restriction to every open cell is a homeomorphism. Each CW complex in the definition above is called a tile type. In complex for a subdivision rule is a two-dimensional CW complex which is the union of its closed two cells. together with a continuous cellular map whose restriction to each open cell is a homeomorphism. We can subdivide into a complex by requiring that the induced map restricts to a homeomorphism onto each open cell, is again uncomplex with map. By repeating this process, we obtain a sequence of subdivided complexes with maps. Binary subdivision is one example. The subdivision complex can be created by gluing together the opposite edges of the square, making the subdivision complex into a torus. The subdivision map is the doubling map on the torus, wrapping the meridian around itself twice and the longitude around itself twice. This is a fourfold covering map. The plane, tiled by squares, is a subdivision complex for this subdivision rule, with the structure or map given by the standard covering map. Under subdivision, each square in the plane gets subdivided into squares of 1/4 the size. Quasi-isometry properties. Subdivision rules can be used to study the quasi-isometry properties of certain spaces. The graph consists of the dual graphs of every stage, together with edges connecting each tile in with its subdivisions in. The quasi-isometry properties of the history graph can be studied using subdivision rules. For instance, the history graph is quasi-isometric to hyperbolic space exactly when the subdivision rule is conformal, as described in the combinatorial Riemann mapping theorem. Applications. Islamic Giri tiles in Islamic architecture are self-similar tilings that can be modeled with finite subdivision rules. In 2007, Peter J. Liu of Harvard University and Professor Paul J. Steinhardt of Princeton University published a paper in the journal Science suggesting that Giri tilings possessed properties consistent with self-similar fractal quasi-crystalline tilings such as Penrose tilings predating them by 5 centuries. Subdivision surfaces in computer graphics use subdivision rules to refine a surface to any given level of precision. These subdivision surfaces take a polygon mesh and refines it to a mesh with more polygons by adding and shifting points according to different recursive formulas. Although many points get shifted in this process, each new mesh is combinatorially a subdivision of the old mesh. Subdivision rules were applied by Canon, Floyd and Parry to the study of large-scale growth patterns of biological organisms. Canon, Floyd and Parry produced a mathematical growth model which demonstrated that some systems determined by simple finite subdivision rules can result in objects whose large-scale form oscillates wildly over time even though the local subdivision laws remain the same. Canon, Floyd and Parry also applied their model to the analysis of the growth patterns of rat tissue. They suggested that the negatively curved nature of microscopic growth patterns of biological organisms is one of the key reasons why large-scale organisms do not look like crystals or polyhedral shapes but in fact in many cases resemble self-similar fractals. In particular, they suggested that such negatively curved local structure is manifested in highly folded and highly connected nature of the brain and the lung tissue. Canons Conjecture. Canon, Floyd, and Parry first studied finite subdivision rules in an attempt to prove the following conjecture. Canons Conjecture. Every Grom of hyperbolic group with a two-sphere at infinity acts geometrically on hyperbolic 3 space. Here, a geometric action is a co-compact, properly discontinuous action by isometries. This conjecture was partially solved by Grigory Perelman in his proof of the geometrization conjecture, which states that any Grom of hyperbolic group that is a 3-manifold group must act geometrically on hyperbolic 3 space. However, it still remains to show that a Grom of hyperbolic group with a two-sphere at infinity is a 3-manifold group. Canon and Svensson showed that a hyperbolic group with a two-sphere at infinity has an associated subdivision rule. If this subdivision rule is conformal in a certain sense, the group will be a 3-manifold group with the geometry of hyperbolic 3 space. Combinatorial Riemann mapping theorem. Subdivision rules give a sequence of tilings of a surface, and tilings give an idea of distance, length, and area. In the limit, the distances that come from these tilings may converge in some sense to an analytic structure on the surface. The combinatorial Riemann mapping theorem gives necessary and sufficient conditions for this to occur. Its statement needs some background. A tiling of a ring gives two invariants, and, called approximate moduli. These are similar to the classical modulus of a ring. They are defined by the use of weight functions. A weight function assigns a non-negative number called a weight to each tile of every path and can be given a length, defined to be the sum of the weights of all tiles in the path. Define the height of under to be the infimum of the length of all possible paths connecting the inner boundary of to the outer boundary. The circumference of under is the infimum of the length of all possible paths circling the ring. The area of under is defined to be the sum of the squares of all weights in. Then define. Note that they are invariant under scaling of the metric. A sequence of tilings is conformal in the above sense. Then there is a conformal structure on the surface and a constant depending only on in which the classical moduli and approximate moduli of any given annulus are comparable, meaning that they lie in a single interval. Consequences. The combinatorial Riemann mapping theorem implies that a group acts geometrically on if and only if it is Gromov hyperbolic. It has a sphere at infinity, and the natural subdivision rule on the sphere gives rise to a sequence of tilings that is conformal in the sense above. Thus, Canons conjecture would be true if all such subdivision rules were conformal.